Hello guys, today we will discuss about dependence of Fermi level on temperature for an extrinsic semiconductor. Previous class we have seen the variation of Fermi level with respect to temperature in case of an intrinsic semiconductor. If you have not go through that once so that you will have a better understanding. All of you know that there are two types of extrinsic semiconductor, that is N-type and P-type. This classification is based on the types of material we are using for doping the intrinsic semiconductor to make it extrinsic semiconductor. Further, the position of Fermi level depends on two factors, that is temperature and impurity concentration, that is the concentration of dopant atoms we are using for the doping purpose. Today we will see how the Fermi level changes its position with respect to variation in temperature. First we will see for an N-type semiconductor, the expression for the Fermi energy in case of an N-type semiconductor is given as EFN is equals to ED plus EC by 2 plus KT by 2 log ND by 2 into 2 pi m star KT by h square whole to the power 3 by 2. What are the quantities over here? These you all know that EC is the energy corresponding to bottom of conduction band. If conduction band lies over here, this EC is the bottom of the conduction band. ED is energy corresponding to donor level. As we have discussed in our previous lectures that N-type semiconductors are doped with group 5 elements which are having extra electrons and they donate those electrons to the semiconductor. That's what the energy level where those extra electrons lies is known as donor level, and it is denoted by the notation ED. So ED is the energy corresponding to the donor level in N-type semiconductor. How much donor impurities we are adding to the intrinsic semiconductor to make it N-type semiconductor, that concentration of the dopant is known as donor concentration and it is represented by ND. K is the Boltzmann constant, T is temperature in absolute scale, M star is the effective mass of electron and H is Planck's constant. We have seen all the notations over here, and this is energy band diagram. This is top of the valence band, this is the bottom of conduction band, and ED is the energy corresponding to donor level. Now we will see what is the position of the Fermi level that corresponds to the Fermi energy and how it changes with change in temperature. Let us consider the situation where the temperature is equals to absolute zero temperature. If I am substituting T is equals to 0 over here, the total value of this factor encircled within this circle is equals to 0. If this total term is equals to 0, what will be the value of EFN? That is equals to ED plus EC by 2. Only this term will be there, this is 0. Right? Let us see where it lies in the energy band diagram. This is the energy direction. This is the top of the valence band, this is bottom of the conduction band, and this is our dopant energy level. Now EFN is equals to ED plus EC by 2. That means it should lie just halfway in between ED and EC. So if you will donate EFN by this dotted line, then EFN lies just in between EC and ED. This EFN is the Fermi level for N-type semiconductor. And this diagram what we have drawn over here, that is at absolute 0. So at 0K, the Fermi level of an N-type semiconductor lies exactly at the middle of the donor level and the bottom of the conduction band. Now we will look into the situation where the temperature is other than 0 Kelvin. Here I have taken the temperature in the x direction and this is the energy. If I am increasing the temperature slowly from 0 Kelvin, you can see there is a small gap between this donor label and conduction band, and these are the electrons of the dopant atoms. They are loosely bound to the semiconductor and they need this much energy, that is the gap between EC and ED. This energy is much smaller as compared to our forbidden energy gap, that is difference between EC and EV. These electrons lying at the energy level ED, they need this much energy to move to the conduction band. So if I am increasing the temperature slowly, what will happen? These electrons will start moving to the conduction band. The electrons at the dopant label, they will slowly move to the conduction band as I am increasing the temperature slowly. If these electrons are moving to the conduction band, what will happen to the atoms left at the donor label? They are losing electrons, that means they will become positively charged. So the atoms which are losing the electrons, they will become positively charged. That's what here I have written, that as the temperature increases, more and more donor atoms are ionized. Ionized means as they are losing the electron, they are becoming positively charged ions. Now if I am continuously increasing the temperature at a certain value of temperature, some of the bands in the semiconductor, they will break and electron hole pairs will be generated. Once those electron hole pairs are generated and energy supplied is more than the forbidden energy gap, then these electrons, they will start moving to the conduction band. That means with increase in temperature, slowly more and more electrons will move from the valence band to the conduction band, leaving behind holes in the valence band. So further increase in temperature results in generation of electron hole pairs due to breaking of covalent bonds, and the material tend to behave in intrinsic manner. The electrons, those are moving from the valence band to conduction band, those numbers will increase slowly with increase in temperature, and at a situation will arise that the number of electrons present in the conduction band is almost equals to the number of holes present in the valence band. Then that time they will start behaving like an intrinsic semiconductor. So if they are behaving like an intrinsic semiconductor, now we will see what will happen to the position of the Fermi label. We all know that the position of the Fermi label in case of an intrinsic semiconductor lies just in between EC and EV, that is halfway in between EC and EV. So EFI, if this is the Fermi energy for an intrinsic semiconductor, the position of this Fermi energy is just at the halfway between EC and EV. So it is at the middle of EC and EV. In the previous slide, we have seen that the position of the Fermi label in case of an N-type semiconductor is just between EC and ED. So this is the exact position at T is equals to 0 Kelvin. Now slowly as we are increasing the temperature, it will move and slowly it will come down and it will behave like an intrinsic. That means the Fermi energy will go to merge with the Fermi energy of an intrinsic semiconductor. So this is the position of the Fermi level of an N-type semiconductor with variation of temperature. At higher temperature, slowly it will come down and it will go to merge with the intrinsic Fermi energy. The Fermi energy gradually moves towards the intrinsic Fermi level EFI. That is, with increase in temperature, slowly this Fermi energy starts moving. Initially, it was just at the middle of EC and ED. With rise in temperature, it is slowly coming down and is finally going to merge with the intrinsic Fermi energy. This is what we have seen in the previous slide, that as temperature increases, the Fermi level gradually moves towards the intrinsic Fermi energy, that is EFI. Now suppose we change the concentration of the dopant atoms. What will happen to this position? If I am increasing the dopant concentration, it will take some more time to behave like an intrinsic semiconductor. Thus, if I am increasing the dopant concentration, it will move to the intrinsic Fermi energy, but that trend will start at a higher temperature and it will come to the Fermi energy at a higher temperature compared to the previous one. So here this blue one is for higher concentration, this red one is for lower concentration. If the concentration is less, then it is moving towards the intrinsic Fermi energy at a lesser temperature, and if the concentration of the dopant is high, then the Fermi level moves towards the intrinsic Fermi energy at a higher temperature. So the temperature at which the Fermi level moves towards intrinsic Fermi level increases with carrier concentration. Now coming to the Fermi energy in p-type semiconductor, this is the expression for the Fermi energy in case of a p-type semiconductor. This EV is the energy corresponding to top of the valence band. EA is energy corresponding to acceptor level. NA is acceptor concentration. K is Boltzmann constant, T is temperature in absolute scale, mH star is the effective mass of hole, H is Planck's constant. To have an p-type semiconductor, we need to dope the intrinsic semiconductor with group 3 elements, and group 3 elements are lack of electrons. That means they can easily accept an electron because their valency is 3. They need one more electron to have that stable state. We have seen that the acceptor level lies just above the valence band. So this is the energy corresponding to acceptor level. This is bottom of conduction band, and EV is the energy corresponding to top of valence band. Now we'll see how the Fermi energy or the position of the Fermi level changes with respect to temperature in case of a p-type semiconductor. First we will look into the condition where the temperature is equals to 0 Kelvin. So at 0 Kelvin, this total term is equals to 0 irrespective of this logarithm value, because this t is equals to 0. So the second term over here is 0. That means what will be the value for EFP? That is EV plus EA by 2. So if it is EV plus EA by 2, this is the position for EV, this is EA. So what will be the position for EFP? Right, it is just at the middle of EA and EV. This is the position for Fermi energy in case of a p-type semiconductor, and that too the condition is at absolute 0. Thus at 0 Kelvin, the Fermi level of a p-type semiconductor lies exactly at the middle of the acceptor level and top of the valence band. Now we will look into the situation if I am increasing the temperature. Here you can see there is a small gap between the acceptor level and the valence band. So with a small rise in temperature, these electrons from the valence band, which are due to generation of electron hole pairs, they will move to the acceptor level, and these electrons, they will combine with the acceptor atoms, and if these electrons are getting added, the atom will become negatively charged. So if the atoms are negatively charged, that means they are getting ionized. So as the temperature is increasing, slowly more and more electrons will move from the valence band to the acceptor level. As the temperature increases, more and more acceptor atoms are ionized. And still if I am increasing the temperature, what will happen? This electron gets more and more energy, and if the energy is more than the forbidden energy gap, they will start moving to the conduction band directly. So now slowly we are getting electrons in the conduction band and holes in the valence band. So with rise in temperature, slowly the p-type material is converting into intrinsic semiconductor. Thus, further increase in temperature results in generation of electron-hole pairs due to breaking of covalent bonds, and the material tends to behave in intrinsic manner. For an intrinsic semiconductor, the Fermi level lies just between the conduction band and valence band, and with rise in temperature, this p-type semiconductor is slowly behaving like an intrinsic semiconductor. We have seen that at absolute zero, the position of the Fermi level in case of a p-type semiconductor is just at the middle of EA and EV. So this is the position at absolute zero, but as we are increasing the temperature, the material is behaving like an intrinsic semiconductor, so the Fermi level will slowly move towards the Fermi level of an intrinsic semiconductor. Thus, this is the variation of the Fermi level with variation of temperature. The Fermi level gradually moves towards the intrinsic Fermi level EFI with rise in temperature. Now we will also see if we are changing the concentration of the dopant element, that is the acceptor elements, how the Fermi energy will change its position. Suppose I am increasing the dopant concentration, that is the acceptor atoms. In that case, what will happen? More electrons will get absorbed over here, and it requires some more electrons to compensate the nature of p-type semiconductor and to behave it as an intrinsic semiconductor. So if it requires more electrons should move from the valence band to conduction band, that means the temperature should be more. Thus, if I am increasing the dopant concentration, the trend will be same, but it will start at a higher temperature and it will move to the Fermi energy at a higher temperature compared to the previous one. Here this blue one is for higher concentration of dopant and this red one is for lower concentration. What we have concluded is the temperature at which the Fermi level moves towards intrinsic Fermi level increases with carrier concentration. This is the carrier concentration. It starts moving towards the Fermi energy at a lesser temperature, and if the concentration is more, then it will move to the Fermi energy at a higher temperature. This is how the Fermi level varies with temperature in case of p-type and n-type semiconductor. Hope you understand the concept. Thank you all. If you have any queries, you can write it in the comment section. Please like, share and subscribe my channel so that more and more people can get the benefit from this initiative. Thank you all.